Hi, everyone. Today we're going to talk about logistic regression for the first time. So moving on from ANOVA and multiple linear regression, we're going to talk about the situation where we have a binary or categorical response rather than a continuous response. So in particular, as I was just saying, we've seen before how we can model a quantitative response using ANOVA or multiple linear regression, but now we're going to be talking about when we have a binary outcome, so an outcome with two possible levels. And we're interested in modeling the probability of this categorical outcome or likelihood of an event occurring. So some examples that might be used in real life, we might be wondering if whether or not a student is accepted to med school is affected by their GPA. So the likelihood of them being accepted using their GPA as a predictor. That's something we can use logistic regression for. If we're looking at the chance that a person has an auto accident in the next year, knowing their age, that would be another instance where we could use logistic regression. So in the first setting, GPA is our predictor. It's a quantitative predictor. And acceptance into med school, yes or no, is our binary response. In example 2, a person having an auto accident in the next year, yes or no, is our binary response. And their age, the person's age in years, is a quantitative predictor. So these are both just one predictor logistic regression models. And just to name a couple more examples, so it might also be of interest to look at if the risk of Down syndrome in a child is related to the maternal age, so the mother's age. I think this is a slightly known thing that the risk of Down syndrome is slightly higher as age increases for the mother. So this is something we could explore using a logistic regression model. Another setting would be if first-generation college students are less likely to graduate within 5 years. So in this case, our outcome is whether or not a student graduates within 5 years, yes or no. That's our binary outcome. And our predictor is actually a categorical predictor. Is the student a first-generation college student or not? Did either of their parents go to college? So we can also use categorical predictors in logistic regression to model our categorical response. Okay, and so for logistic regression, we still have y denoting our response. And this is going to take on values of 0 or 1, where we have 1 represent the reference category. So sometimes yes, and 0 being no. Although this is not how it always has to be, yes or no, with yes being 1. You could have no be represented by 1 and yes be 0. It just depends on the setting, the context, and what exactly you want to model. For example, maybe we want to model if Augsburg beats St. Thomas in football, we could say y is yes equals 1 yes if Augsburg wins, and 0 if Augsburg does not win. But maybe if we're a St. Thomas student, we want to model it the other way around. So y equals yes if St. Thomas wins, so 1, and 0 otherwise. So it just depends on your perspective and what exactly you want to model. And it just affects the interpretation of the coefficient estimates and estimated probabilities for the model. So we're going to start today by looking at just simple logistic regression. So this is referring to that it's a logistic regression model with just one predictor. That's why they call it simple. Just like the linear regression case, where simple linear regression was the case where we just have a single predictor. That's why it's called simple. It's not that it's computationally simple. It's just that there's one predictor. And again, this predictor can be quantitative or categorical. And specifically, we're going to be modeling the probability that y, our response, equals 1. So typically, we denote this with pi, the Greek letter, the Greek letter for p, representing the true probability of success, the probability that y equals 1. And probabilities in general, not just for logistic regression, but in general, probabilities are constrained to be between 0 and 1. You can have a probability of exactly 0 or 1, so these should really be inclusive, but that's not too important here. In general, it's important just to know that probability always must be positive, and it cannot be greater than 1. So this probability of success, most people are familiar with, even who haven't taken a statistics course, what a probability means. Odds is a little bit more foreign. It's a little bit more specific to statistics, so people might not be as familiar with that if you haven't taken a course covering logistic regression or similar concepts. So the odds that y equals 1 is defined for logistic regression as the quantity pi over 1 minus pi. Okay, so it's just this ratio of the probability of success over the probability of failure. Okay, so for an odds, if the odds of success are 3, then it is 3 times as likely that there is a success than there is a failure. That's how we can interpret that's the interpretation of the odds. So it's the ratio of the likelihood of success to the likelihood of failure. Okay. And we can further define the log odds just to be this exactly as it sounds, the log of the odds here. Okay. And notice that since a probability is always between 0 and 1, the probability of success is always going to be positive, and the probability, or 0, and the probability of failure is also going to be positive. So this ratio, the odds ratio, will always be positive. Okay. So when we're talking about the log here, there's sort of two commonly used logs. There's the log base 10 and the natural log, which is the log base e. Okay. For logistic regression, we use log base e. Now, this is due to some statistical theory, but it just like you could use log base 10, but nobody ever does that. There's some statistical theory reasons for why we choose log base e here. So always for logistic regression, just assume we're using log base e. And if you're curious about why that is, I would suggest taking a statistical theory course, a stat theory course, as they call them. So here, this log odds transformation of the probability of success pi is called the logistic or logit transformation. So sometimes people call this the logit link that we're using for logistic regression. Okay. And so sort of in a similar setup to multiple linear regression, we are modeling a response, sort of a function of the response on the left side using this linear combination of the x's. So in this case, we have intercept plus slope times x equals the log odds. Okay. And notice we don't have, so this is our assumed regression model, our theoretical regression model here. Notice that we do not have an error term. So we only have the residuals or error term in multiple linear regression when we're assuming normal errors. But here for logistic regression, we don't have this error term. And this again comes down to the statistical theory of how this model is set up. It's not that we always have perfect fit for our predictions for logistic regression. It's just that the theoretical model that we're assuming does not involve residuals here. The distributional assumption is solely based on the response y, rather than the residuals like before. Okay. And so there's sort of two ways you can think about this assumed model. You can think of it as we're modeling the log odds here as this linear combination of the predictor variable, or if you solve for pi here, so setting e to the power of something sort of undoes the natural log. So if you go through that algebra and solve for pi here, you would find that pi is equal to this function of the x, of the predictor variable here. And they call this like the inverse logit function, because this is the logit function, and the inverse of it that solves for pi is the inverse logit function. Okay, so you can sort of think of it too as that we're estimating a probability or modeling a probability through this form. But people more commonly write it as the logit form here because that more closely resembles regular multiple linear regression. Okay. And so if we plot this inverse logit of the linear combination of the predictor, the linear predictor, sometimes they refer to these two terms added here. Sometimes they call it the linear predictor. If we look at a plot of the inverse logit of the linear predictor here, which is the probability of success, we can see it's sort of this S-curve shape. Okay. And it's sort of hitting what they'd call in math these sort of asymptotes at 1, where I have this dotted line, and 0. And so what will happen is, as the linear predictor here gets bigger and bigger, this S-curve, the inverse logit function, will get closer and closer to 1, but it will never exactly reach it until this is actually infinity. So for any finite linear predictor, this is not quite 1, but it just gets closer and closer to 1. And similar with 0, it never gets quite 0, but as it goes to minus infinity, this will get closer and closer to 0. So in this way, because we're using this functional form to model our data, we'll actually constrain all of our estimated probabilities to be between 0 and 1, which is desirable because a probability has to be between 0 and 1. So we want this. This is a nice property to have, that we won't get an estimated probability of like 5, because that's not sensible. So this is a good property to have for our model. So a reasonable question to ask might be, why don't we just model our response using just a regular linear regression model? So why is 0 or 1 in how it's coded when we model this? So technically, that's a quantitative response. That's a number. So we could just say, hey, fit a regular multiple linear regression model and see what happens. And there's nothing stopping you from doing that. You can totally do that. But we'll look at what's the issue with when you try that. So let's consider an example. So suppose we are looking at modeling whether an email is spam. So we're going to denote that as a success, y equals 1, or not, y equals 0. So it's not always the case that a success is a good thing. In this case, a success, email being spam, is a bad thing. Using the number of capitalized characters in the email. So the idea is that, like, when you get those fake emails, that's like, hey, you've won $10 million, and it's all in caps, it's more likely to be spam because regular people don't write emails in all caps. So anyway, so we can model the probability, for example, of an email being spam, which is something Google might want to do, to flag it for you using the number of capitalized characters. So plotting the response by the number of capitalized characters using a scatter plot, it looks like this. So all the emails either are spam with a value of 1 or they're not with a value of 0. So this scatter plot sort of looks a bit different than we're used to seeing for linear regression. But again, we could still fit a straight line here using regular linear regression and see what happens. Right off the bat, though, we do see if there's a linear relationship present between number of capitalized characters and whether it's spam or not. Doesn't really seem like a linear relationship. So that already seems violated in terms of the assumptions here. Okay. So now to fit a linear model, we're going to use slightly different code. Before we've seen just the LM function. Now we're going to use the GLM function, which stands for generalized linear model. And this will give us equivalent results to the LM function when we specify family equals Gaussian in this way. So this is saying assume we're using a Gaussian or a normal response here. Okay. And the reason I'm using this function now is because we use GLM to fit a logistic model. So fitting a regular linear model, here we get this regression output. And for 300 observations, 300 emails, and we see that the number of capitalized letters is positively related to the likelihood of it being spam or not. Okay, so that seems reasonable as a sort of quick sanity check. So we get like if we think about predicted values that we're going to get from this, we're just going to get some number. It doesn't have to be between 0 and 1 necessarily. Linear regression doesn't constrain boundaries on our predicted values in that way, like logistic regression does. But so how do we decide if a prediction is corresponding to us thinking the email is spam or not? Well, one thing we can do, which I think is the simplest way and most common way people would do this, is just say if a predicted value is less than 0.5, which corresponds to a 50-50 chance, then say we're predicting not spam. The email is not spam. And if the predicted value is bigger than or equal to 0.5, then say we estimate that the email is spam. That's what that prediction is corresponding to. So there we go. Using this approach, we can get estimates for whether an email is spam or not using multiple linear regression. But one thing that we learned before, sometimes we need to make sure our assumptions are met if we're going to do inference about coefficients or confidence intervals, stuff like that. We need to make sure our assumptions are valid for this model. So looking at the residual by fitted plot, this certainly does not seem great. So constant variance, here the variance is pretty small in terms of the spread of the points, and then all of a sudden over here, the spread is huge. So constant variance does not appear to be met here. And more egregious, more obvious an assumption being violated would be independent residuals. So residuals that are closer, observations that have closer predicted values here have much more similar residual values. There's this clear pattern in the points. That's not good. So that's suggesting independence of the residuals is violated as well. So we already see linearity was questionable or not met. Constant variance does not appear to be met. And then independence of the residuals does not appear to be met. So sort of 3 strikes already against the assumptions being met. Looking at the QQ plot, just for the heck of it, to check normality, again, we have a lot of points straying really far away from the dotted line here. So that seems to suggest normality is not met either. So violating another assumption. And just to check, looking at a histogram of the residuals, which should be bell-shaped, for the data, if normality is met, we see there's actually like it's like a bimodal distribution. We have 2 different values, 2 different distributions here. So this violates the normality assumption as well. There should be only one bell curve if this assumption is met. So just further evidence, none of these assumptions appear to be met. So we cannot do any sort of statistical inference for this model. But I want to note, from an academic perspective, this seems awful to do, fitting a multiple linear regression model to this binary response. But we can get predicted values. We can fit the model. We just can't do statistical inference. But sometimes you're only interested in predictions. So sure, you can go ahead and see how this model does. There's nothing technically wrong with that in practice. So this is a model to consider. Chances are it won't do very well with predicting observations in the future for data not in our current data set, but I mean, as long as you're not trying to do statistical inference, it's okay to use. But let's consider using our logistic model, our classification model, instead as well. Although first we'll look at how this linear regression model does on this current data set. So plotting our prediction, our estimated line, regression line, here's what we can see the predicted values are for y given x. So it just doesn't really seem like it fits the pattern in the points that well. If we look at 0.5, which is corresponding to the cutoff where an email will be considered spam or not, we go all the way over here. It's actually off the plot, but it looks like somewhere around like 30 or 40 capitalized characters. If there's that many or more, it's going to start estimating that the email is spam. But for this data set, actually none of the emails hit 50% yet. So and we can see that by plotting the estimated classes, the estimated or predictions of whether the email is spam or not. We can see what this linear regression model predicted. It predicted 0 cases to be spam. And it predicted all 300 to be not spam. Whereas the truth, the observed, there was 15 that were actually spam, but then the model predicted they were all not. But there was 15 that actually were spam. So it got 15 predictions wrong, 285 correct. So the correct values are on the diagonal. They call this a confusion matrix. That's what they call this type of table that visualizes the truth here versus what you predicted for the classes. That's a confusion matrix again. So this model is not very good. It predicts the same thing every time for our data set of it not being spam. So that's not great. It's not a very good model. So a lot of room for improvement. So let's try a logistic model and see how that does. So we're going to fit it using this GLM function again. And instead of specifying family equals Gaussian for a linear model, linear regression model, we're going to specify binomial because we're assuming our response is a binomial random variable. Okay, and looking at that model output, we again can see that the higher the number of capitalized characters in the data set or for the email, the higher the likelihood that the email is spam. And specifically how we interpret this value for logistic regression is we'll say since beta hat equals 0.787, the odds of, we say for every additional capitalized character in an email, the odds of the email being spam multiplied by e to the 787, which I'll find using R real quick here. So e to the 787, R tells us is about 220. So we round. So since beta hat is 0.787, for every additional capitalized character in an email, the odds of the email being spam multiplied by about 2.2. Okay. So that's how we interpret the regression coefficient for this simple logistic regression model. Okay, and plotting our estimated probabilities for this logistic model based on the number of capitalized characters in the email. This green line is the predicted values for our linear regression model from before. This black line is corresponding to our logistic model that we just fit. So you can see here how it's not linear anymore. We're getting this S-curve shape again for our predicted probabilities. So that's what logistic regression gets us. And since we have this zeros and ones, this seems to fit the data a lot better here. Again, we don't really calculate residuals, but if we think about the amount of error for each prediction, the logistic model is getting these spot on, okay? Gave these a very low probability of being spam, and they were not spam. So it's doing a much better job than the linear regression model here based on this plot. And then also up here, once the number of characters gets really high, it's giving it a very high probability of being spam. Okay, and the cutoff is somewhere about here at 0.5. So this is where the logistic model from here onto the right starts thinking it's more likely that the email is spam than not. Okay. So you can see how this logistic model certainly seems to fit the data a little bit better. And making a confusion matrix to see how well it did on our data set that we just fit it to, we can see it actually detected some of the emails that were spam. So out of the 15 total emails that were spam, the logistic model detected 7 of them. So 7 out of 15 times it correctly caught a spam email. And it still got most of the non-spam emails correct. So only twice did it think an email was spam when it actually was not. So it got 2 of those wrong, but then it got 7, was able to catch 7 emails that were actually spam. So depending on your goal, depending on the outcome, this might be considered performing much better than the linear model. I do want to point out, though, that it certainly depends on the context, right? So this is just email. So maybe incorrectly identifying an email as being spam when it's actually not is not too big a deal. But when you're thinking about like screening for certain types of cancer or some sort of setting like that, it's really important to think about what a false positive or a true positive means in those types of testing situations. So, it's certainly very important, obviously, for like cancer screening that we do catch when things are true positives. For example, if we're defining it as cancer being the outcome of interest, then we certainly want to make sure we catch anything in our testing procedure. So anyway, main takeaway, it depends on the context, but here for emails, this model seems to be doing much better. Okay, but how can we formally compare which model is better? So we've seen this before, how we can use AIC or BIC to compare linear regression models. For generalized linear models, GLMs, which encompass which linear and logistic models are a subset of, we can compare these types of models using AIC and BIC as well. Okay, so getting the AIC for both linear and logistic and BIC, we get these values where the log fit is for the logistic model, MLR for the linear model. And in general, we want to select the model that minimizes AIC or BIC. Usually they'll give the same model, but not always, for which one they imply is the best. So actually here, since we want to minimize it, AIC and BIC are suggesting we should pick the multiple linear regression model. So it is what it is, that's what these metrics are suggesting we use as our final model. But I do want to note, based on looking at the plot, the fact that the linear regression model can give predicted values not between 0 and 1 for the probabilities. It just doesn't seem like it's a very good model to use. So we shouldn't always just look at AIC, BIC, just pick the one that has the lowest value and just stick our head in the sand and say, yep, that's our model. Don't care what else is going on. It's important to still think about other contexts to the problem, especially if you're using very different models like this. So using like a continuous Gaussian response versus a categorical response, we want to be careful. It's still valid to compare them in terms of AIC and BIC, but I think I've mentioned this before, another metric, so if you're a little iffy on this, which I am here, I'm skeptical, another metric that you can use to compare models of different types like this is cross-validation error. So I mentioned this in a previous video, talking about how we can use cross-validation error to assess how well our model will do on unseen data. So as a quick reminder, cross-validation will set aside some data that we don't use for fitting our model, and then we fit our model on the rest of the data, and then see how well we predict on that subset of observations that we left out, with the idea being that if our model does really well in predicting data that it wasn't fit on, then it'll probably do well for unseen data in the future. Okay, and so specifically one way we can do this is using leave one out cross-validation, LOOCV. So this is where we, so for example, here we have 300 emails. So we fit 300 total, say, logistic models, where each one is fit on 299 observations, 299 data points, and we leave out a different observation each time. So there's 300 different ways we can do that, 300 different emails we can leave out. And then we see how well the model does in accurately predicting the status of that one left out email. Okay, so we'll get 300 total predictions, see how well the model does in predicting those 300 different emails. Okay, and we can do that for the multiple linear regression model and the logistic model. And the idea being we want the model that is the most accurate in predicting for these left out emails, the ones left out in our data set. Okay. And so we see here's where AIC and BIC disagree with this cross-validation. So multiple linear regression was accurate 95% of the time. Okay. And 95% of the emails in the whole data set were not spam. So we knew that model was always just pretty much predicting not spam. So that's why it's getting 95% accuracy. The logistic model, on the other hand, correctly predicted almost 97% of the emails for whether they're spam or not. So this is where the leave one out cross-validation, since we're getting a higher accuracy for the logistic model, is doing better. So personally here, I would select the logistic model. I think it makes the most sense by far to select the logistic model here, even though AIC and BIC suggested multiple linear regression. Okay, so it's just another one of those things that these metrics are not always perfect. They just give you a suggestion, and you should still use broader knowledge in the area to make an assessment about which model is best. Okay. So that's all for logistic regression today. Thanks, and we'll see you next time.